copy down the theorem on the back, and then you're going to have to fill in the blank.
Meg, is she here today?
She was here. Yeah. What's after g of x? Yes. This is an upside down A, and it's the short form for all. Okay? One of your math professors in college might use this. So if this is true for all x. So all right, so your job is to now read it and tell me what goes in the blank. Check out everybody in the class. What? No. This is a guarantee that you got to get it. No. Okay, do you have an answer to this? This is actually a theorem in your book. Xander, you got something? That f of x equals L. Is that what you got? Okay. Anybody else get that? Why do you say that is? Okay. So, okay, you're totally on the right track. The limit as of f of x as x approaches c is equal to L. Like that? Anybody thinking that one? Okay, that is the correct answer. Okay. Now, why? Well, if we look at it from a visual standpoint, let's explain what this looks like. So what is that? What does this first thing mean? h of x is less than or equal to f of x, which is less than or equal to g of x for all x, in some sort of interval that contains C, except possibly a C itself. Okay, so I've got some interval. I don't know. I'll go from here to here. Okay, that's my interval on x. And there's some random C value inside here. And then this is supposed to be true. So this is how you interpret this. You say, okay, I've got some h of x, and it looks like this, whatever. Okay, this is my h of x. And every y value for h is less than every y value for f, which is less than every y value for g. Okay, so you can say f of x can do anything it wants to here. Okay, so this is then f of x. Okay, here h of x is less than f of x. That's what we mean by that. Okay. And the last one, g of x has to be greater than this, but then I got to look ahead and I got to see this. Ooh. And the limit as x approaches c of h of x and g of x is both L. So I don't know.
Is it supposed to be ABC?
ABC. No. Because it's my interval is a to b, and then c is a point that's inside of a. What I do know is the limit as x is approaching c is equal to L for my h function, and it's also equal to c for my g function. This is how you translate a rule like this. You got to think it through, and this is part of our technical reading. I can't do every single one of these for you. Eventually, I got to pass the torch on to you. Okay. And seeing that you're all Greek today, passing the torch is, sorry. Okay, so the limit here, we don't know what's going on exactly right here. This point may or may not exist, but the limit for both g and h are the same. Well, look at what has to happen to f. Since f has to be in between these, I can't draw this any way that I want to. Right at c, I have to make it so that this little f function has to go right in between. You sort of have to squeeze it in between, okay? And that's why it's called the squeeze theorem, okay? So this is showing for, if you know the limits on these two outer ones and you know this one is in between it, then the middle one has to have it. This is actually one of the ways that that sine of x over x limit that we said yesterday that was proved. Okay? All right. Be able to translate technical writing like this into something that's meaningful. All right. To the board. We have, we're going to do a bunch of problems now for the rest of the class. We're going to take a look at lots of different random ones. I'm trying to remember with the two rules that we learned yesterday. The ones that I asked you to memorize. Okay, what was that again? One was the limit as x approaches 0 of the sine of x over x. That's equal to 1. And then all the variations of that are 1. And the second one is the limit as x approaches 0 of 1 minus the cosine of x over x, and that was equal to 0. You got to put those in your brain and memorize those, because those will be on the AP exam. All right, the three problems that I have up here are all variations where we might use that, but they're not exactly the same. Okay, So look at this right here. This is the sine of 7x over x. Okay? That doesn't quite fit that sine of kx over kx, okay, that we wrote down yesterday. It's kind of close, but the only thing is we're missing a 7 right here. Okay? We don't have the 7. Okay? So how can we figure this out? If we could manipulate this in some way, you see, this is like I'm taking the limit of that function. Okay? Now, in the past, you've modified functions to benefit yourself. In other words, you multiply some things top and bottom by things in order to get something else. So what I'd say is I need this to match this. So what I'm going to do is I'm going to multiply that bottom by 7. Just because. Okay? Now, can I do that? No, I can't. Unless I multiply the top by 7 also. Okay? So what I'm going to say is if I multiply the top and the bottom by 7, then what I did was I multiplied by 1. But it was just disguised as 7 over 7. Okay? So I've got this. Now, the power in this is we learned a property yesterday of limits that if this 7 right here is actually a constant that's multiplied by this function. So I can really take it out. In other words, I'm going to write the step here. This is equal to the limit as x approaches 0. Now look at what I'm going to do here. 7 times the sine of 7x over 7x. This I'm rewriting now as this. You see that? So as long as now I can write this as this, ooh, we've got something, we got 2 rules. One was, if you look back at your limit properties, the limit as x approaches 0 or any number of k times f of x, you can take the k out. So you can pull out that constant. So this is really the same as 7 times the limit as x approaches 0 of the sine of 7x over 7x. And we learned that yesterday that this whole bugger is equal to 1. So the answer is 7. Okay. Now, I showed you all the steps, how to get there exactly. I also used the constant rule where we pulled out the 7. But technically, you could have said, remember that one? The limit of a product equals the product of the limits. You could have done that one too. The limit as x approaches 7 times the limit as x approaches 0 of the sine of 7x over 7x, you still get 7 times 1, which is 7. Same thing. Okay, so that's one way to handle something like that. Let's do another one. Okay, look at that. How do you suppose or propose we do that one? Remember, we're in our algebraic way of trying to handle these limits. Okay? Anybody know what that looks like, graphing it without a calculator? Okay, it's a little bit hard to figure out. Okay, so we're going to solve them algebraically. Okay, any ideas? Okay. Is that, no? Okay. So what I think I'm going to do here is I'm going to take this and I'm going to see if I can write this somehow into the form of one of these. Okay? So I'm going to say this is the limit as x approaches 0 of, well, I got 3 times x on the top. And sine squared x means that's the sine of x times the sine of x. This is all just algebra. taking this and I'm saying that's what this is equal to. It's 3 times x, and sine squared x is just sine of x times sine of x. Okay? Now look back at what we did here. Okay? The goal is to kind of divide and conquer, kind of separate these things into things that make sense. Well, I would look at this and say, well, limit as x approaches 0. The 3, I can write that as the 3, it's really 3 over 1. Because I'm looking at the rest of this and I spy x over the sine of x. And I see x over the sine of x. You see that? So if we kind of like filter it out, sift through and break it apart into things that matter, what's the limit as x approaches 0 of the 3? 3. What's the limit as x approaches 0 of the x over sine of x? 1. Same thing here. 1. So the answer is 3. See that? We're using our algebra to kind of divide and conquer. This is really where, I didn't write the step in here where it's the limit of the product is equal to the product of the limits. So we're taking each one of those individually. Okay, let's do this one. Number 3. Go copy it down and try to do some work on it. Try to break it apart. Tell me what. Oh, tell me if anything good comes from that one. Okay, anybody got any ideas? What can we do with this one? Bummer here is that this has a sine of 5x and this is a 7x. Okay? I think you might be going in the right direction. Jamie?
Did we take the 4 out then?
Sure. We can take the 4 out. Did everybody see that we can take the 4 out? This is a constant. It's just being multiplied here. So I can write this as 4 times the limit as x approaches 0 of the sine of 5x over 7x. Okay? Yeah. If you look closely at this, the 7, okay, the 7 is, again, couldn't you write it as 1/7 out here? So technically, watch this. I'm going to erase this. I'm going to write this as 4/7 where I take out the 7. This 4 over 7 is just simply a fraction that could be multiplied by the sine of 5x over x. Look carefully at that. This is all this is algebra. So 4/7 is a constant that we can pull out, and the remainder is sine of 5x over x. Okay? All right, how do we finish this one off? We're so close, though. Harry. Right. So we multiply the top and bottom by 5 because you do the matching thing first. I need a 5 here, so we put the 5 here. To compensate for that, we multiply by the 5 here. Okay. So what does this become? Well, the 4/7 is still outside. This is multiplied here, so we're multiplying. And then I'm going to actually pull this 5 out, so it's 4/7 times 5. And then if you want to write the limit, it's the limit as x approaches 0 of the sine of 5x over 5x. And that's going to be 1. Anytime you see this, okay, and it's got to be of the form of one of those that we said, bam, the limit is 1. So here, it's 4/7 times 5 times 1, so the answer is 27. Yeah.
When you say diagonal cut, after you take the 4 out, is it going to work that you just take that 5/7 out and then multiply it?
And multiply it. It depends. If it always looks like this, yes. Okay? But it won't always look like that. There may be some kind of variation. So, but I suppose, look at this. I'm going to try writing a general rule here. Okay, so we're going to propose the Smithyman rule for limits. And it would look something like this. The limit as x approaches 0 of, watch what I'm going to do here, a times the sine of bx over cx, where a, b, and c get to any number that they want to be. This is how mathematicians write general rules. They say, ooh, I wonder if we could make, if there's a pattern here. Now watch what happens here. If I were to write this like as a proof, I'd say, okay, that's equal to this. This is really a over c times the sine of bx over b. See what I did there? A over c is really a fraction that's multiplied by the sine of bx over x, my bad. Okay? So, well, that a over c, that comes out here. So we say a over c times the limit as x approaches 0 of the sine of bx over x. Okay. You guys with me? And then I can say, well, this guy just needs a b, which means I'm going to multiply this by a b. That compensates for it. Which means my final answer is going to be a over c times b times the limit as x approaches 0 of the sine of bx over b, x, which we know is 1. So the answer here, ab over c, is going to always be the answer if it always looks like that. Where a and b, where the 4 and the 5 and the 7 can be any number.
Would it be the same after the 2 over c times 5?
If it was, say it again.
2 over c, only you take the a out and then b over c.
Yeah, b over c times a is the same as a over c times b, or ab times divided by c. Okay? So if you have one that looks like that and you want to memorize that rule, go for it. Or just work it out. Okay. All right. Backboard. 2 new problems. Okay. Try numbers 4 and 5 on your own right now. The best thing I can do is teach you the process for how to solve a problem like this. Because it's impossible for me to show you every single problem. So that's what you should be focusing on doing, is how to go about the problem. Okay, did you get a big donut for the number 4? Did you put sprinkles on it? Ooh, it's making me hungry. Oh yeah, donuts. Bring donuts tomorrow. Friday. Yeah. Well, the answer won't always be, because I could have something like this.
Okay, so what if it's not?
But this part will always be 0. Yep. So you just have to be aware of everything that's around it. This answer would be 5. Okay, you get this number 5? Little manipulation, right? Okay, I'm gonna go for it. If you're done, you can go ahead and try that one. So, hey, I'm gonna take that 3 out right away. Let's see. Right? That's how I would break that apart. There's 4 signs of x, signs of 2x on the top. There's 4 x's being multiplied on the bottom. Is this good? Okay. So every one of these 2x's need a partner. So I'm going to multiply 2 and 2 and 2 and 2. Right? And so if I just do this, I'm bad. Okay, can't do that. I've changed the problem. So in order to not change the problem, 2, 4, 8, 16, I can multiply the numerator by 16 here. And so final retail answer is, it's 3 times the 16 and then times all these ones. So it's 48. Agree? Okay. So every problem is different. You just got to go about it and separate it and see what you can get out of it. That's the deal. Okay. Last one. 0, no, 1. Okay. Can we plug it in? Can we plug in pi over 4? You got to check that first. Why can't you? Sine and cosine of pi over 4 are both the same, so that's going to give me 0. Bam. Because we all know what happens when that happens. Okay. So, divide and conquer, switch it up. What can we do with this? Tangents, right? Convert the tangents. Okay, let's try that. So let's convert our tangent to sine over cosine and see where this gets us. So the limit as x approaches pi over 4 is 1 minus the sine of x over the cosine of x all over the sine of x minus the cosine of x. I like to be annoying. Okay, that was fun. Yeah. Yeah, somehow, if we got to somehow get this. I would look at this and say, hey, maybe the cosine, maybe we should try to get a common denominator here or something. One thing we could do is, if I got a common denominator, I'd write cosine of x over cosine of x. Right? So watch this. I'm going to write this as cosine of x over cosine of x. Okay? Because that's 1. And then this is going to get me limit as x approaches pi over 4 of cosine of x minus sine of x over cosine of x over sine of x minus cosine of x. I multiplied this one by cosine of x over cosine of x. See that? And my tangent, I converted to the sine of x over cosine of x. All right, does this get us anywhere closer? Well, this is where the big division symbol is, okay? Because this is still my numerator, okay? So, well, we just go forward. We say, okay, what do I got? This is the limit as x approaches pi over 4. And so if it's this divided by this, just for my own sake, I'm going to write this over 1 so I don't mess that up.
Did you multiply by the reciprocal? Like 1 over the sine of x minus 1 over the
Yep,
cosine?
good. That's exactly what we're going to do. So I'm going to take this guy. This is the numerator. I'm just going to leave it as it is. Cosine of x minus the sine of x over the cosine of x. And we're going to multiply by the reciprocal of the denominator, because that's how we divide fractions. So it's 1 over sine of x minus cosine of x. Can we cancel anything? Dog nabbit, look at this. This is cosine of x minus sine of x. Is it the same thing as the sine of x minus cosine of x? Is x minus 3 the same as 3 minus x? Okay. They're not the same, but they're like really close, aren't they? Okay. We're going to make an observation here. Okay, so look at this. This is an observation. If I have 3 minus 5 over 5 minus 3, okay, this is what I've got here. This guy and this guy, just the order is switched around. So 3 minus 5 is negative 2. 5 minus 3, that's negative 1. Okay, let's try that again. 16 minus 3 over 3 minus 16. Negative 1 again, isn't it? So it's negative 1. So really what I'm saying here is a minus b over b minus a is always equal to negative 1. So what this means is this over this can cancel, but I replace it with negative 1. Bless you. So what does this become? Limit as x approaches pi over 4 of, what do I got left over? I got a negative 1 over the cosine of x. Okay, can we plug in the pi over 4 now? Yep. So this is, notice this is the moment where we drop the limit notation because I'm plugging it in. As soon as you plug it in, you drop the limit. So it's negative 1 over the cosine of pi over 4. And what's the cosine of pi over 4? Square root of 2 over 2. So it's negative 1 over the square root of 2 over 2. And let's simplify this. We shouldn't really leave a compound fraction like this. What's negative 1 over the square root of 2 over 2? Negative 2 over the square root of 2, and then rationalize, simplify that, because it can be way simplified. Way simplified. Huh? Negative square root of 2 is correct. Okay? And just a little side note, the square root of 2 over 2 is the same as 1 over the square root of 2. So if I'm going to take the reciprocal of this, it's the same as taking the reciprocal of this, which is the square root of 2. Okay. What's the lesson learned here? Sometimes the problems take a little bit longer than others. Okay? If there's one thing that I would really hope that you learn throughout the course of this year, which will help you in no matter what you do, it's perseverance. It's to never give up. Okay?
Doing like those solid daggers.
It's good though, right?
Wait, this is